All right, second part of this series is talking about the other critical spatial data model. We're going to talk about raster data, and then I'll follow up with describing some of the important properties of spatial data. So first, a quick review that data can be both qualitative and quantitative. And when we're talking about quantitative data, we generally have both discrete and continuous data. Like we talked about in the last set of slides, the discrete data is suitable for vector points, lines, and polygons. But when we're mapping continuous data, raster data is more appropriate. We're talking about things that are continuous on the landscape, like precipitation, elevation, soil erosion, things that can exist everywhere, or can be measurable everywhere. And maybe you're saying, now wait a minute, what about things like soil type or vegetation? We can also, quantify things like that, or at least describe things like that. And yes, you can. And I'll talk about that in a second. We can model a lot of things, including discrete features. Also think about streams and lakes. Those are discrete features, but guess what? We can also model those with raster data. So rasters become really powerful in their own way, and I'll show you some of the tricks that we can do with raster data. But I do think it's helpful to start thinking generally about the types of data and then think about the best or most efficient way of digitally representing them. Okay, the raster data model. Think of it as a grid, like a picture, a set of pixels where there is complete coverage and best suited to model phenomena that is measurable everywhere and also varies continuously over a surface. So the most common things we see with raster data are elevation, temperature, rainfall, but we can also model things like solar radiation, noise levels, change over time in landscapes, and things like vegetation. It's a regular set of gridded cells, and the values correspond to the characteristics of the phenomenon, the measured values or the estimated or interpolated values of something that's being measured across the landscape. And I just want to ask you one quick question, following up on what we just talked about in the last lecture series. What do you think is the clearest thing wrong with this legend? Actually, there's a lot of things wrong with this legend. Number one, the precision is ridiculous. In a legend, you want these to be a ballpark for people. This kind of precision is out of control and inappropriate. And also, what are the units of measure here? Don't ever put a number in a legend and don't include a unit of measure. That's just poor form. Okay, raster attributes. Here's the biggest difference between raster and vector data, and it's just important. We don't have a row in the attribute table for every cell. That would be crazy. Instead, we treat this information or this data more like a histogram or like a PDF, a probability density function, where the unique values are calculated and then a count of each value is stored in the attribute table. So does that look familiar to you, that it's more like an unclassified histogram? The values and the counts of the shared values. So how many cells in this raster surface, if this is the size of it, store the value of 5. There's 4 of them, and we go through and actually find them and count them. Here they're being each unique value is given its own color, and we can see that there are 5 of them. Cells where we have no data, either interpolated or measured, contain a storage value that represents no data. So there has to be something accounting for every cell. We don't have a gap here. Now that doesn't mean that we can't have holes in our rasters. We can mask them and do all sorts of things. But for our purposes today, rasters are a set of grid cells. They're all the same size, and each one contains some value. But the attribute table is called a value attribute table, a VAT. There's a value, a unique value, and then a count of how many cells share that unique value. This is what will tell you it's a raster attribute table. So discrete raster models can be used to represent categorical data. So this is kind of a classic DEM. This is the same area showing land cover. So vegetation, it could be urban, it could be agriculture, undeveloped. It can be described in a lot of different ways, but basically for the value attribute table, the value is still a number. It has to be a number. But the number is a key that's going to represent some kind of land cover description. But it's important to know that any statistical calculations or any operations done to this raster are going to be done on that value that's categorical. So you have to be very careful. You can't run averages, for example, because you can't average open water and urban and get an in-between value that represents something that's in between open water and urban. It doesn't work like that. So you just have to be very careful when you're working with categorical rasters that you control the kinds of mathematical operations you're doing on it. Okay, where do we get raster data? Satellite images, aerial photographs, scanned maps. We can actually stick a paper map in a scanner and turn it into a photograph, basically. We can also convert vector data into rasters. So this is what the Mississippi Delta in Louisiana looked like 2 months after the Deepwater Horizon British petroleum oil spill. It's a satellite image in that we're collecting multiple wavelengths. The red indicates plant cover. The shades of white and blue represent the water, and the bright white represents the oil slicks. So we can do really cool things with satellite imagery using more than just real color. This is a seaweed farm in Bali, Indonesia. It's pretty interesting. They harvest a ridiculous amount of seaweed. It's like 50,000 pounds of seaweed per month. They extract it from the water and they lay it in the sun and dry it for 3 to 7 days. Isn't that interesting? My kid eats a lot of seaweed, so I thought that was pretty fascinating. All right, so raster data models. Every cell, like I said, is the exact same size. Now, between different rasters, cells can have different sizes, but in any given raster surface, it's a very uniform grid. Every cell, like I said, has to have a value. The values can be integer or real numbers. Categorical data is always going to be an integer. Real numbers means it's got a decimal and can float. And then, like I said, cells with no value are assigned no data. So this is kind of a cool way to think about it because, like I was saying, we can map discrete surfaces. Let's say we have a landscape and we have a measured value. Maybe it's a weather station and we gathered precipitation measurements at these locations. We can then interpolate between them and fill in the grid to get the continuous surface. But we can map a discrete surface. We'd have known measured values at these locations and no data in between them. But it's still a grid, right? Okay, so it's important to know that when we are representing geographic features with a raster and we're mapping discrete features, that cell size is really going to drive our understanding. And as an instructor, it's going to reflect, for me, your understanding of the data. So, for example, it's very common to map streams with a raster, but the cell size can't be taken as the stream's width. The stream could be the Mississippi, or it could be the Mississippi River, which can be miles across, or maybe it's a mountain stream that's 4 feet across. Well, if this is a 30-meter raster, that means that the cell is 30 meters across, and now we're representing a mountain stream as something that has a width of 30 meters. So you have to be very careful. Discrete data is precise at all scales, but the precision can be erroneous as when we take a line to represent a road. So it's the same thing with rasters. We have to be careful about that cell size and understand that it's creating another disconnect with reality. So Linear features are mapped as a series of connected cells. A point feature is represented as a single cell, and again, if the point is representing a city, and now all of a sudden the city is being represented as something that's 30 meters by 30 meters, be wary. And then areas are groups of connected cells with shared raster values. All right, so looking at a real world data set here, here's a little watershed in northern Utah. If we look at the elevation information about this little watershed, the elevation information is, this is a little bit confusing because it's being displayed with kind of a three-dimensional model called a hillshade, but what's being represented here in black and white is actually being drawn in green to purple on the map, so this is a little bit confusing. But for this watershed, the low value is 1,400 meters, the high value is 2,818 meters. If we open the attribute table for this raster, which we can do because it's an integer, we're going to see a value and a count. This is how we know that it's a raster, value and the count. So the row ID just means that however many rows there are that many unique values, unique elevation values in this data set. But what it's telling us is the low value of 1,400, there are 83 cells in this raster that share that elevation. We can look for the max here. It looks like we've got kind of a bell curve distribution. We could sort this based on the count and get the most common elevation type or elevation value for this raster. But this value count means it's a raster attribute table. Okay, let's take a look at some data properties really quick. And first I'll show you a slide and then we'll go into ArcGIS. So raster cells are described in resolution. Just like a picture, a high resolution photograph has a very small pixel. And a coarse resolution photograph has a very large pixel. It's going to be blurry or grainy. Same thing for rasters. We describe the size of the cell by the resolution, and the resolution is the size of the cell or the pixel. Okay? The units for resolution are defined by the raster's coordinate system. It's either going to be degrees, meters, or feet, and you can find that in the layers properties. Just a heads up, rasters, because rasters need to be a square, you need to be really careful with the coordinate system or the framework that we're defining them in. So if you have a raster where the units are decimal degrees, you need to change that, and we'll talk about that in the advanced class. But just be wary of rasters that you see are in decimal degrees. Okay, so if you right-click on any data set in the, let me see if I can find it here. Nope, I cannot. In the contents pane of ArcGIS, right-click and go to the properties. It opens the properties for the rasters. If you go to the source tab, that's where all the really good stuff is. So you can open up these different sections, but the Raster Information Tab tells you how many columns and rows there are in the grid. Hopefully that makes sense. A one-band raster just means that each cell is storing one value. Here's the resolution for the raster. The cell size, X and Y, should be the same. This means that it's 9.3274837 units of measure wide and tall. Floating point means that it is able to store a decimal place, real numbers, and some of these things we don't need to get into right now. If we scroll down a little bit, there's an extent tab under the source. The extent tab is the first place you can see the units of measure. So if we go back, this means the resolution for this data set, each cell on the ground measures 9.327, etc., meters wide and tall on the ground. We would call this a 10-meter DEM. That's what this is. It's an elevation data set. So this raster has a resolution of 10 meters, but the exact width and height of each cell is 9.327. And when I say width and height, I mean on the ground, not up high elevation. Okay, and this extent is really important to look at, I think, because it shows you that the units are meters, and these are great big values, and that's real because these are usually like a distance from the equator. So this would say that the northernmost extent of this raster is 4.5 million meters north of the equator, and the southernmost extent is 4.5 meters north of the equator. So if you distanced or separated these, differenced these, you'd see how big this raster is on the ground from north to south. And then this maps the eastern and westernmost extents. Then the last thing I want to show you is the spatial reference, which we'll get into in the advanced class, but this defines the grid work, or the grid or framework that we're going to lay these extents on. So let's quick jump into ArcGIS, and I'll show you some vector data as well. All right, here's ArcGIS Pro, and I have 3 data sets in here. One is a road data set, and then I've got an elevation data set that's floating under here, so you can see the white values are the high mountains, and then the black down here is the Salt Lake. And then I've got a land cover data set underneath, which is all the crazy colors. Okay, so if I look at the properties, and you can't see this because of course it's off the screen, and go to the Source tab, we can see that it's a raster. This is where the raster is stored on my computer, and the vertical units are meters, so that's the elevation. So that's the units for these guys here. If I go to Raster Information Band, Statistics, and Extent, the extent value is like I was showing you. Units are meters. The raster information is where we can see that it's storing one value, that's elevation. This has the same resolution as the one I just showed you in the example. And then finally the spatial reference. This is the most common coordinate system used in the state of Utah, NAD 83 UTM Zone 12. Now, notice here that it's got units of meters. That's for the coordinate system. It also has units of degrees, but this is lower down than this. This projected coordinate system is the coordinate system, and if you see this, NAD stands for NAD, North American Datum of 1983, and if we scroll down, that's repeated here. This is built into this. This projected coordinate system is the framework, so meters is the unit, and that's why you see the meters here and not degrees. So this data set is good to go that way. Let's quick look at the land cover properties. Again, Source tab, and we'll go to the raster information. And notice here we have a different cell size. Here the cell size is 30 by 30. And you can see if I go to the extent, the units are meters. So this means that these cells are 30 meters by 30 meters on the ground. So it's a coarser data set. It's less detailed information for this land cover data set. All right, and I can show you that if I zoom in here. Let's see, let me turn off this guy. And we'll look at just the land cover. So notice you can actually see the size of the cell, and I'm going to zoom in a little bit more. Cancel. If I grab my measure tool, I can get a really coarse measurement, and you can see it's approximately 30 meters on the ground. And if we were to do that for this guy, which is going to be harder to do because I don't have the extreme kind of color ramp like you do, but if we were to measure across a cell on the elevation data set, it would be approximately 10 meters across each cell. I can try and find the edge of one here. Let's see if that works. So 10 meters for the elevation cells. Okay, and then let's take a look at the vector data just for comparison. Again, I'm going to the properties, which you can't see. Okay, so under the Source tab again, you can see that now it's telling you it's a shapefile feature class and not a raster. Again, this is where it's stored. It gives you the geometry type. It's a line. That makes sense. Yeah, none of that really matters. The extent, again, it's projected. We've got units of meters. And then the spatial reference. So it's also in the same coordinate system. But here in the data source, you can see it's giving you everything that we talked about. It's telling you what the geometry type is. It's telling you it's a shapefile feature class. And if we open the attribute table for these, last but not least, so for the roads, you can see that each feature has, let me zoom to layer here so we can see, whoops. Okay, this roads data set, I could select one. Let's see if we can see it. No, too small. So it's this tiny little segment right here is this row. But it's telling me that it's in Ogden, it's Highway 39, it's a portion of it. Polylines are stored as segments, so it's not the entire road. If we were to sort this, we could probably find, oh, not custom sort, we could probably find all the Highway 39s. Let's try a select by attribute just for the fun of it. I'm just, what was it called? The Cardo code? No, it was called the full name, is equal to, let's see if we can just force Highway 39 in there. Ooh, there are a lot of them. Highway. Okay, so let's close this. And so it looks like there are 48 different road segments called Highway 39. And if we zoom out a little bit, yeah, okay. So Highway 39 is comprised of a bunch of different road segments. Each one has its own record in the attribute table, and you can see that there's a lot of stuff that's stored. None of it's all that interesting. We've got surface directions, yeah, probably a length calculation in here somewhere. Okay, so that's vector data. That's a select by attribute. There are 13,000 segments in this road attribute table, but that doesn't mean there's 13,500 roads. As you can see, each road is divided up into little segments that makes up a whole road. We can't open an attribute table for this raster because it's a floating point. There are too many unique values, but the land cover we can open an attribute table for because it's categorical, so the value is going to be an integer. So we can get a very constrained set of unique values here, and then here's our count field. So the value in the count is what tells us this is a raster attribute table. These descriptions or variables are appended to this value. This is the kind of the key for this whole data set is the value field. If we sort this descending, our most common count is value of 110, which represents open water. So for this data set, and if I turn these off and just look at the land cover, I'm going to zoom to layer, the most common cell is open water, which probably makes sense. The second most common description is intermountain basins. Let's see if I can get that to fit here. Sagebrush, something, something. Yeah, so I think that's all I'm going to say. If you have any questions, let me know, and thanks for your attention.